In this presentation, we examine Newton's third law of motion. So Newton's third law of motion is one that you've probably heard before, but maybe just not in terms of Newton's third law. So Newton's third law is often described as, for every action, there's an equal and opposite reaction. So Newton's third law says that whenever one object exerts a force on a second object, that second object exerts an equal but opposite force back on the first. So basically, when objects interact with one another, if object 1 exerts a force on object 2, then object 2 exerts a force equal and opposite back on object 1. So let's examine these forces and these interactions. So here I have this picture of a person and a block, and we're going to sort of look at what's going on between those two. So the first thing about Newton's third law is that forces always exist in pairs. And you should be able to identify, if you have one force, what the pair to that force actually is. Those pairs of forces always act on different objects. So if you're going to look at Newton's third law, you have to be able to identify two separate objects, and you have to be able to look at the forces that are being applied between those two objects. And that's going to help us identify a pair of forces according to Newton's third law. The pairs of forces that are created always have exactly the same magnitude, same size, and they're always directed opposite one another. So if I look at my picture over here, I have a force exerted on the block by the person. So I've written this as the force that the person exerts on the block. Well, when the person exerts a force on the block, it turns out that the block exerts an equal and opposite force back on the person. So that would be considered a pair of forces according to Newton's third law. So how can the block and the person move if there are these two forces that are equal and opposite that are acting on these objects? And so this is often confusing to people because they think that if forces are created in pairs and they're always equal and opposite, then they're going to cancel each other out and that objects can't move. But the key to this is that the pairs of forces always act on different objects. So if you look at the forces that are on a specific object, an object can have a force exerted on it and not have a pair, according to Newton's third law, acting on that same object. So let's examine the block and then the person separately. So here is the person and there's part of the block. So we're just looking at the person, and then here's the block and there's the hands of the person. So there is a force from the person acting on the block, pushing the block to the right, and in turn, the block pushes back on the person. I know these are a pair of forces according to Newton's third law because, well, first of all, they are equal and opposite. They're acting on different objects, but more specifically, if I look at the description of the force, this is the force of the person on the block, and if I switch block and person over here, this is the force of the block on the person. That tells me that they're a pair of forces. So if I can write out a description that says this is the force from this object on that one, and then I switch them, that's going to tell me that that's a pair of forces. Those pairs of forces act on different objects. And so if I just examine the objects individually, they may have other forces exerted on them. So for example, if the person is actually walking and pushing the block, then the person's foot is pushing on the ground, and the ground is pushing back on the person. That's another pair of forces, but we can't see the other pair that goes with it. But the person's foot pushes on the ground pushes back on the person. That propels the person forward. So there's this force that's propelling the person forward, which is actually larger than the force that the block is applying to the person. In the same regard, if the block is sliding across the floor, it's being pushed by the person, and maybe there's some friction, but that frictional force might be less than the applied force that's on the block, and so the block can actually move forward and it can accelerate. There's some additional forces. Of course, there's the weight of the block, so that's the force of gravity or the earth that's pulling on the block. And then there is a contact force because the block is in contact with the ground, and that's the force of the ground on the block. So notice we have ground on block and ground on block. So we have to be careful. These are different types of forces. One is a force that's parallel to the motion, this frictional force, acting opposite the motion but parallel to the ground, and that's because of the rubbing. And the normal force is perpendicular to the ground, and that's due to the fact that, that the surfaces are pushing together. So I could do the same thing over here. I have the weight of the person, which is the force of gravity on the person, and then I have a normal force, which is the ground on the person. Again, a different ground on the person versus over here where the person is being propelled forward. So those are different directional forces. But one of the things that's key here is that you still have a pair of forces, but to identify those pairs, you have to look at two objects. And the only pairs of forces I have in this picture are the force of the person on the block and the block on the person. Those are the only two I can interchange those descriptions and get the pair. All right, so let's see if we can identify some third law pairs. I have a dog. The dog is at rest on the table, and I want to know what are the forces that are acting on the dog, what are the interacting objects, and what are all the third law pairs. So if the dog is sitting on the table, I need to look at the forces that are acting on the dog. So I isolate the dog from the environment, which basically means I isolate the dog from everything else, the table, the earth, everything else. And I can draw what's called a free body diagram. And all that means is I'm going to draw the forces that are just acting on the dog. So I know that the weight or the force of gravity is acting on the dog, because the dog is on the earth, and so gravity is pulling on it. This is the force that the earth exerts on the dog. The dog is sitting on a table. So there's also a contact force between the table and the dog. So there's this force that the table exerts on the dog. Those are the two forces, and the only two forces that are acting on the dog, because it's not moving and it's just sitting on the table. There's no static friction because nobody's pushing on the dog, and so we have those two forces. We can use the equilibrium rule, since the dog is sitting there and not moving, and we can say that the sum of the forces along the vertical direction have to be 0. I have a positive contact normal force, and I can add that to the weight of the dog. So in this picture, the normal force would have to equal the weight of the dog. Now, the normal force and the weight are equal forces. They're oppositely directed. So is it true that the support force and the weight are third law partners? They are equal. They are opposite. Why is it that they are not third law pairs? And the easy answer to that is that both of those forces act on the same exact object. If forces act on the same object, even if they're equal and opposite, they are not considered a pair of forces. Remember that we have to be able to exchange this. In order to determine what is the pair of force for this contact force, I have the force the table exerts on the dog. I would have to have the force that the dog exerts on the table. So let's see if we can identify those other pairs of forces. So the interacting objects that I have in my picture are the dog, the table, and the earth. And we're not going to worry too much about the interaction between the table and the earth, just what the dog is interacting with. So if I separate and I just look at the dog and the table, and then I look at the dog and the earth, I can identify these third law pairs. So I know that the table is exerting a force, an upward contact force on the dog. So the pair for that one would be that the dog is also pushing down contact-wise on the table, and so there is a normal force of the dog on the table. These are a pair of forces according to Newton's third law. They're acting on different objects, and I can easily tell they're pairs because I can replace table on dog with dog on table. In the same regard, I have my dog here. The table is missing from the picture, but the dog is still sitting on the table. And I have this gravitational force, which is the force of the earth on the dog. It's the gravitational pull. It's the weight of the dog. There has to be a pair to that. And the pair to that is that the dog actually exerts a force on the earth. There is an attractive force between the dog and the earth. And so those are also a third law pair. They don't have to be touching one another. This is that force at a distance, that field force where objects can exert forces on one another at a distance. Now, obviously, if we took the table away, the dog would fall. And so we know it would accelerate towards the earth, but the earth doesn't move towards the dog. Well, that's because the earth has a huge amount of mass. So that small little force that the dog is exerting is insignificant compared to the size, the mass of the earth. Whereas this force is significant because the dog's mass is relatively small compared to the size of that force. All right, so here we have another example where we have different masses. So I have a mother and her child here, who's wearing an LU shirt, Longwood, is they're both at a local park and they're going rollerblading. And the mother gives the child a push. So she pushes the child to the right. What is the motion of the child? Well, if she gives the child a push to the right, and we're using rollerblades because we're going to assume that there's very little friction. So it's kind of like ice skating where she gives the child a push to the right, so the child is going to move to the right. Well, what's the motion of the mother? If she pushes the child to the right, is she going to move? Will she move to the right? Will she move to the left? Will she not move at all? And the answer is that she's going to move to the left. And the reason that she moves to the left is because when she pushes on the child with some force, the child actually pushes back on her with the same amount of force. So the force on the child is to the right, causing the child to move to the right, and the force on the mother is to the left. The child doesn't actually physically have to push on the mother. It's just the fact that she's pushing against something and that causes her to move in the opposite direction. So this could have just as easily been a crate, and if she pushed on the crate, causing the crate to move across the ice to the right, then the mother would move to the left because the crate would create a force back on her. Equal forces, opposite direction, acting on different objects. Are they going to experience the same acceleration? They experience the same force because of Newton's third law, but they will not experience the same acceleration. Acceleration depends on the force applied and the mass. They both experience the same force, but the mother, we can assume in this picture, the mother has much larger mass. So the mother's acceleration will be less, and the child, which has a smaller mass, will have a greater acceleration. So same force, but different acceleration based on the mass of the object. So here's a couple of quick quiz questions, just to see if we understand this idea of Newton's third law. So I have a fly that's traveling, so a little fly, you know, like something you want to swat away. So a fly is traveling to the right, and it collides with a fast traveling automobile traveling to the left. The force exerted on the fly is greater than the force on the automobile, the same as the force on the automobile, and less than the force on the automobile. So if the fly exerts a force on the automobile exerts an equal and opposite force back on the fly. So it's the same force. It doesn't matter that the fly is a tiny mass and the automobile has a huge mass. If they interact with one another and they exert forces on one another, it's going to be equal and opposite according to Newton's third law. Same fly traveling to the right, and we have the fast automobile moving to the left. The acceleration experienced by the fly is, well, they have the same force, but just going back to the previous example with the mother and the child, the fly has a very small mass. So it's going to have a greater acceleration as compared to the automobile, which has a very large mass. So we basically now have three laws of motion. We have Newton's first law of motion, which is often called the law of inertia, that an object at rest is going to remain at rest or moving in a straight line at a constant speed unless it's acted on by some net force. We have Newton's second law, which is often called the law of acceleration, which says that when you apply a net force on an object, the object is going to accelerate, and that acceleration is going to be directly proportional to the net force, more acceleration, and inversely proportional to the mass. So the larger the mass, the smaller the acceleration. And then finally, Newton's third law of motion, which is often called the law of action and reaction. Basically, whenever one object exerts a force on another one, that second object is always going to is always going to exert an equal and opposite force back on the first. So we've got these three laws of motion that we can apply now to look at the motion of objects, and we can even look at some problems.